Okay. Uh, Hello, good morning, everyone. So today we're going to learn about the Turing machine. Turing machine is the most powerful computer. That is the last chapter of your syllabus, and we're going to learn exactly how Turing machine looks like, and what is the working of the machine, what is the architecture of the machine, with the help of one example and some animations. And then we are going to solve multiple problems of designing of Turing machine. So today's lecture is very important lecture where you are understanding about the working. Once you understand and visualize how Turing machine is working, it's very easy to solve these problems. Okay, so pay your attention properly and try to understand what is the Turing machine. In case of any doubts, you can ask me the doubts by unmuting yourself or by writing the chat in the chat box. Okay. So I think the screen is visible to you. Can you see this? The slide? Is the slide visible to you?
Yes, ma'am.
Okay. So Turing machine is a machine that is, this is the definition of the Turing machine. Turing machine is a machine which is a combination of seven elements, that is Q, sigma, rho, then delta, Q0, F, and capital B. Okay, similar to push down machine, Turing machine is also a combination of seven elements: Q, sigma, rho, delta, Q0, F, capital F, and capital B. Okay, what is the difference here is that there in push down machine we have Z0. Z0 as the stack symbol. But here we don't have a Z0 as a stack symbol, we have a capital B as a blank symbol of the tape. So we can write this capital B as a blank symbol, or we can use a small b with a slash on it as a blank symbol. So different books or different designs, they have different notations. So I'm going to use the notation as capital B to indicate a blank symbol, or you can have a small b and over the small b you can have a slash on that b. Matlab you erase, cancel it. Okay, so that is also a blank symbol. And here there is no stack. Okay, here there is no stack. So we are having this row as a set of finite set of symbols which can be written on the tape. Okay, you have the input tape. On the input tape, a read head can perform read and write operation both. So this row contains a set of symbols that can be written onto the tape, input tape. So it can be also a output tape now for this particular machine. So Q is a finite set of states, sigma is the finite set of input symbols, and rho is the symbols which can be written on the input tape. And delta is a transition function. This is the exam. This is the transition function, that Q into rho is equal to Q into rho into L or R or no, where L indicates left, R indicates right, and no, N indicates no direction. Okay, so I'll explain you rho and delta again with respect to the another slide. Q0 is the initial state, F is a set of final states belonging to capital Q, and capital B is a blank symbol. So this is the definition of Turing machine. I know that this understanding of rho and delta may be a problem right now. So we'll see that with the help of an example. So right now you can understand for this particular slide that Turing machine is a machine that is most powerful machine. It is equivalent to your computer, digital computer, and it is a combination of seven elements. Only Z0 is replaced with capital B. All other things are same of push down machine, but the meaning of rho and delta is different. Okay, delta is a transition function, state transition function, and rho is a set of symbols which you can write on the input tape. Okay, so we'll see one example. Okay, now as this diagram is showing, as shown in this diagram, this is a particular a state transition. This is a single state transition. It is not a complete machine. Okay, it is a single. Whatever is seen in this particular diagram is a single state transition. Like state is transited from state to Q2 to Q5. Okay, so what is this is animated image. Okay, so right now the machine is here. This is a read head. This is a read and write head. Okay, till now for the finite state machine and push down machine, this was only the read head, and read head can only perform a read operation. Okay, but now for the Turing machine, it is a read head as well as it is a write head. So how it works, like here. Okay, right now here the machine is in the state 2, and in the state 2, okay, now look at here the portion where we are writing the logic. Machine is in the state q2, and in the state q2, if on the input tape, if there is any zero, then what we are saying, that erase that zero and write 1. After writing 1, go to write, and the state is transited from q2 to q5. Okay, so what is the meaning of this particular thing is that here the machine read write head, there is an input tape which is an infinite tape. This is a read and write head. The read and write head can perform read operation as well as write operation on the tape. That is not the case with the other machines. Okay, so now here this red color means it is performing a read operation. Okay, so here it is reading a zero. So if it is a zero here, as per the logic, erase that zero and write 1. So zero is replaced with 1, and then it is moving to right. Okay, so how the machine works is that machine can move to right, or machine can move to left, or machine can remain in the same state. But this is a read and write head, and read and write head is performing read operation as well as write operation. So what it can do is that it can replace 0 with 1, or if there is no change, then 0 is machine will read 0 and it will write 0 back. Okay, so it is always performing read and write operation both. If there is no change as per the logic, then it will read the 0 and it will write the 0 again on the same location. So your input tape is an infinite input tape, and it is divided into multiple cells. One particular cell can contain one bit of information, that is either 0 or 1, or small a, small b, as per the symbols of input, finite set of input symbols sigma. Whatever the symbols are there in the sigma, all the symbols can be written onto the tape, or they are, your input string is made up of the strings of sigma. Okay, and that is already there on the input tape. And what how this machine is working is shown with the help of such a small animated zip image file. Okay, so this read head is performing read and write operation both. So it is reading 0 and it can write 1, means it will replace 0 with 1, and it can go to left, or it can go to right, or it can remain in the same location. Or if there is no change, means if you don't do an if you don't change an input symbol, then it will read 0 and it will write 0 back. Okay, so have you understood this read head can perform it is not only the read head, it is a read and write head. Now it reads the symbol and it writes it back, and if there is no change, it will write the same symbol back on the input cell, but or it can change the symbol. Okay, so I think you have got an idea about this. And now we can say that this Turing machine, now you can see the description here. This is a machine which was invented by Alan Turing, and so the name of the machine is a Turing machine. It is equivalent to the digital computer, and you are having a infinite tape, like infinitely expandable tape. So this is your input tape, and there are zeros and ones are written on the tape. That means your input string is written on the tape. Input string is made up of all the symbols which are belonging to sigma. So sigma contains 0 comma 1, so your string will be made up of zeros and ones. If your sigma is equal to a comma b, then a and b are written on the tape. Or if your sigma is a comma b comma c comma d, then your input string is made up of a b c d. Okay, and your sections may contain 1 or 0, or it can be a blank. By default, on the tape, all the blank symbols are there. So I'm using capital B to indicate blank symbols. So here in the diagram, there is nothing if it is a blank. But I'm going to use a symbol capital B to indicate a blank symbol on the tape. And this is a read write head. And read write head looks at one particular cell at a time. And after looking at a particular cell at a time, it can perform, like here it is looking at a particular cell at a time. It can perform read and write operation. So it reads the symbol and it writes it back, or it reads the symbol and writes the another symbol on the input tape. Okay, this way the machine is working. It is also called as the abstract model of a digital computer. Means it is a mathematical model of a digital computer. Turing machine is a mathematical model of a digital computer, and we see that it is of unlimited capacity. Okay, now these are the features of Turing machine. Whatever are listed down here, this is a diagrammatical representation of Turing machine, and this is a description of the Turing machine. Turing machine is having unlimited capacity. It is having unlimited capacity. Any problem that you can solve by hand, or if you have algorithm for the problem, can be solved by a Turing machine. Okay, so if there is any problem and if the problem has a solution, then it can be solved by a Turing machine. Because in the universe there are many problems which don't have any solution. So if any problem is not having any solution, if it is an unsolvable problem, then it cannot be solved by the Turing machine. But Turing machine can identify that whether the problem is solvable or unsolvable. Okay, that is the characteristics of Turing machine, that it can understand, or it can tell you that whether the problem can be solved by means like, Turing machine can identify whether the problem is solvable or unsolvable. Okay. So I think I'm just I don't know, if I start the presentation, maybe the students are not able to join the meeting. So it is a request that you always have to join on time. And after 5 minutes, like if my lecture is at 9, then I start the lecture at 9:05. Okay. So please, during that 5 minutes of time, you just enter into the classroom. Otherwise, I don't know, when I start the presentation, I think the students are not allowed to enter. It's happening automatically. Okay, now have you are you understanding? This is a very important chapter, and I feel that I should all of you should pay your attention properly. Okay, Turing machine is a mathematical model of a digital computer. It can solve any problem which can be solved by a human. If we have the solution, or if we have the step by step procedure to solve the problem, then that problem can be solved by the Turing machine. So it is the most powerful computer, and the machine has an infinite tape, and the input string means your input is stored onto the tape, and your algorithm is described with the help of delta transition functions. And as per the delta transition functions, this read write head moves to left or right, or it can remain in the same location. It can perform a read operation and write operation both, and that way it is working. Okay, so your input tape is divided into cells of infinite length. This input tape is divided into multiple cells. A cell can contain a single symbol, and the Turing machine is said to be in the halt state if it is not able to transit further. Okay, if the Turing machine cannot transit, it is stuck at a particular location, then we can say that it is halted. Okay, if there is no transition defined in a particular state, like here this is a transition is defined here. If you are in the state q2, and if the input symbol is 0, then replace the input symbol 0 with 1 and go to the state q5. So this is the transition. So if machine is remaining in a particular state, and if there is no transition on any input symbol, or it is not able to transit, then it is said to be it is in a halted state. And if the machine is in the final state, then we can say that the string is accepted by the machine, or it has solved the problem. But if that particular state is not a final state, then we can say that the machine is hanged, and it is in the hang state. It cannot solve the problem, or the problem there's no solution uh, for the particular problem, and it is not reached to the final state. Okay, now it is a combination of 7 elements. Delta is a transition function. This is the example of a delta function. Like suppose the machine is in the state q0. Upon in the state q0, it is reading a small a here, and then it may transit from q0 to q1, and a is replaced with the blank symbol, and it's going to the right. side. Okay, so the meaning of this transition function, like this way you write down the transition functions for Turing machine. Okay, all the machines, they have their own format of writing the transition functions and drawing the transition diagram. Okay, so once you understand and if you are familiar with the notations of drawing the transition diagrams and writing the transition functions, it's very easy to solve the Turing machine, all the designing problems. Okay, so here for the Turing machine, we write the transition delta functions like this, like delta Q0A. That means machine is in the state Q0, and if there is input symbol A, what is going to happen? That machine may transit from Q0 to Q1. So this was the previous state. This is the new state. A is replaced with capital B. Okay, so this is the old the symbol on the input type input. This small a belongs to sigma. Okay, small a belongs to sigma means your input string is made up of A's and B's, and capital B is a symbol that is written on the input tape by the read write head. So capital B belongs to row. Okay, like here you can have A is replaced with small b, means if your small ab is input alphabet. So whatever is here belongs to row, means the symbol that can be written onto the input tape. So row is a set of symbols. Okay, I forgot to write here. Row is a set of symbols which can be written onto the tape. Initially, you are having the input string on the tape, but the read write head can go on writing something. Like your string is made up of zeros and ones, and you can have a machine which will replace 0 with X and 1 with Y. Then X and Y are the symbols belonging to row, and a comma b or 0 comma 1 is a symbol belonging to sigma. So sigma, I think you are understanding the difference between sigma and rho. Please write down in the chat box, are you understanding the difference between sigma and rho? Sigma is the set of input alphabet, means your input string on which your machine is going to work is based on the symbols. It is a group of symbols from sigma. Your input string is belonging to sigma, but your row is the symbols, set of symbols which can be written onto the tape. Okay, for example, I can have 0 comma 1 as sigma, means your string is made up of zeros and ones, and I can have x comma y as row, x comma y as row. So x, and my machine is going to replace 0 with x and 1 with y. So it will start from here, it will replace 1 with y, it will go ahead, it will replace 0 with x, it will go ahead, it will replace 1 with y. Like this, it may change your string from zeros and ones to xy. Okay, in that case, x and y are the symbols which can be written onto the input tape by the read write head. Okay, so that's why your row contains x comma y, and your transition function is q0 comma a is equal to q1 capital B r. So right hand side is always a group of three elements, that is your next state, the symbols which can be written onto the tape, and left or right or n. So L or R or N, either any one of this, either L or capital R or capital N, where L indicates that machine is going to left, R indicates that machine is going to, means read head is going to, read write head is going to right, and N indicates it is remaining in the same location. Okay, so if you remember this particular delta, the way we write, then you can remember how to define it. So delta is q into sigma. So q into sigma means the state from q0. Q0 belongs to capital Q. So q into sigma. Sigma means the symbol on the input tape. Okay. So q into sigma generates uh, q, capital Q. You can write here capital Q first. Capital Q into row into L comma R comma N. So any one of this from the set plus this next state, means it is a group of all these three elements. Okay, some books they write capital B before Q1 and R before Q1, anything like that. But I'm going to use this particular thing. Like so, I can say that here Q into sigma is equal to Q into row into L comma R comma N. Okay, so once you remember this transition, by looking at the transition, you can easily write the definition that this is capital Q, this is sigma, this is capital Q, this is row, and this is L, either L or R or N. Okay, so a set and any one of the element from the set. So this way you write down the delta function, and then we can say that Turing machine is the most powerful. Its power is greater than FSM, PDA, both. And if there is no transition for any input symbol, we can say that the machine is halted. And when it reaches to the final state, it has done the job of acceptor, like it can accept the string, it can calculate something, like it can perform the addition, subtraction, multiplication, division, or any calculation, any type of calculation that we can do by hand or by ourselves. It can act as a recognizer, it can recognize the string and it can reach to the final state. So it can work as a pattern recognizer, or it can perform any computing, and it is acting as a computer. Okay, so it performs everything. Whatever is possible is can be done by Turing machine. It can even do the recursion. Okay, and the difference between other machines is that your read head is performing means read write. It is not only the read head. It is a read and write head. It is performing read operation at the same time it is performing write operation also. Means it is reading the symbol. It may write the same symbol back, or it may write the new symbol back. So the it is a read and a write head. It is reading as well as it is writing. Means if there is no change in the symbol, then it will read zero and it will write zero back. Okay, we don't have to say anything. It will read and write. Write. Both the operations are done at the same time. So it may read and write another symbol, or it may read and write the same symbol, depending on the logic which is defined by us in the delta transition function. Okay. So now here we'll see again one with the help of some animation that how the machine is working. Okay, so here this is an input tape where we write 101 or something like that, and then this is a read and write head. So this can be your read and write it. After reading zero, it is going to write, and here it is ready to read the next symbol, that is one. So here there is like here the state is, here the state is 23. If it is saying that if it is zero, then erase the zero and write one and go to write. Now it is in the state 359. In the state 359, we are saying that if it is there is one, then take no action. So it will not do anything and move to left. Like here. Like here it is, we are saying that the machine is in the state 359. If there is any one, then to take no action and move to left. So machine will move to left, and then it is in the state 20. Okay, this way we can define the working of the machine. Or here, if the state is 23 and if it is zero, then erase zero and write it as one and move to right and go to the state 359. Okay, so this way the machine is going to work. Okay, so let's see one example. Like here also, so now we take one example. Okay, so we have a problem that we have the string double. Uh, we have to check that whether we have to design a Turing machine that accepts the strings of type of a raised to n, b raised to n, c raised to n. Okay, are you understanding? Now there we are going to solve or understand this Turing machine with the help of one example. And the example is design a Turing machine that understands the strings of type of a raised to n small a comma b comma c. So we want to design a machine which can understand the string which is of the type of a raised to n, b raised to n, c raised to n. Okay, I'll write down here the example that we want to design a machine which understands the string of type of a raised to n, b raised to n. This particular example can be solved by a push down machine also. Nahin, here it will be difficult for push down machine. Mm, Here it will be difficult for push down machine to solve this problem. What is our problem is that we are having a string which is having a combination of a's and b's and c, and number of a's should be equal to number of b's, that should be equal to number of c's. So we can write down that string on the input tape, like we are taking the example as 2a's, 2b's and 2c's. And what is the logic here to solve such problem is that you keep that string on the machine. You have the read head, like scanner is called as a read write head. And what is done in this example is that replace small a with capital A. Okay, so let's see now from the beginning. Okay, here capital small a is replaced with capital A. Then this B is replaced with capital B. This C is replaced with capital C. Again, it is going back. For this A is replaced with capital A. Another B is replaced with capital B. The second C is replaced with capital C. And now it is going back. Now it is trying to find out any A. It is not getting any A. So it should not get any small b. It should not get any small c. And here if it is getting a blank, then it is correct. Okay. You must have observed the working of the machine. What is the logic is that small a is replaced with capital A, small b is replaced with capital B, small c is replaced with capital C. Again, it will go back. It will replace the small a with capital A, another b with capital B, and the corresponding second c with capital C. And it is going back. And if it is not getting any A, any B, or any C, that means a number of A's and B's and C's are equal. So after this, if it is getting here blank symbol, then it will end. Okay. Actually, this is animated if I cannot stop it here when I'm posting it on the input tip. But if I can show you without presenting, maybe we can do that. Okay. So here I can stop it. So I'll just stop here. The first small a, small b, and small c are replaced with capital A, capital B, capital C. Now it has gone back and is trying to change the another a. So for this a, it will make this b as capital B and this c as capital C. When it will go back, it should not get any particular string here. It should not get any b here, and then it will get a capital B blank. Then the number of b's and c's are equal. Okay, so now it is this it has changed this. Then now this small a is changed to capital, this will be changed to capital B, this will be changed to capital C. And now it is trying to find out a, it is not getting. It is trying to find out b, it is not getting. And then if it is getting a blank here, like it was shown here, na, it was getting a blank here, that time it will stop by going to the final state. So it is trying to find out, and at the one after one iteration, here it has stopped. Okay, so this way it is going. We are going to solve this problem now. Okay. So before that, I just want to show you like how to when you are designing this Turing machine, what are the different notations that you have to write down. Okay. For example, first you need to write down the definition. This is the definition of Turing machine. This I have explained you. Then you need to write down the description. This is a description that suppose your A's and B's are stored on the input tape. This is a read and write head. This input tape is of infinite length. After reading a symbol, read and write head reads the symbol and writes the new symbol or the same symbol on the tape. It can move to left or right or no move. States may be transited. And in the transition diagram, how to show the transition. In the transition diagram, if you are in the state Q0 and if the state is changed from Q0 to Q1, Then you need to show the transition by showing the arrow. And here we write down the notation like this, that small a is on the tape, small a is replaced with another, the small a, means the same symbol. Okay, small a is on the means the read operation will perform small a read, then it is writing a again with a, means a is replaced with a. So this is the read operation and this is the write operation. They are separated by using a slash. So a is replaced with small a and it's going to write. Okay, so the meaning is here like this. Or if,
Ma'am,
yeah,
some students want to join.
okay, okay. Now you're able to see now the screen.
Yes, ma'am.
Okay. So now here what I'm trying to say is that if you are this is a notation that is to be used when we draw the transition diagram. Transition diagram shows the working or algorithm of the problem. Suppose you are replacing A with X, and if the machine is transited from Q0 to Q1, then we can draw the diagram like this, that Q0 to Q1 there is a transition. There was a small a on the input tape and small a is replaced with small x. So a slash x, and normally small case letters are used to place on the input tape. So your sigma or row contains small case letters most of the time. Okay, that is the notation that is used. And R indicates that it is going to the right side. Read head is going to the right side. Or if you write here capital L, the read head is going to the left. Okay, so you can draw the diagram like this by using such notation. But when you are writing delta in terms of functions, then you can say that here q0 comma a means in the state q0 it is reading a small a. That will result into a new state q1 and the new symbol small a comma r. So RHS is three symbols, LHS is two symbols. Current state is q0, it's reading small a. What is going to happen? It's going to go to the new state, that is q1. A is replaced with small a and it's going to write. So you can write down that in terms of delta. Or here for this particular transition, you can say that it is in the state q0. It's reading small a. Then it is going to the new state q1. A is replaced with x, means this a is changed to x, and it's going to right side. Okay, so what is the difference is that a finite state machine or push down automata doesn't have control over their input. In case of finite state machine or push down machine, we cannot change the input. It can only perform a read operation. Here it cannot perform a write operation. It can only read, and by default after reading it goes to write. After reading it goes to write. After reading it goes to write. Like if finite state machine and push down machine works that way, means here it will read the zero. After reading by default it goes to right. After reading the symbol it will go to right. Then after reading the next symbol it will go to right. So finite state machine and push down machine works with this manner. They cannot perform a write operation. Okay, now here Turing machine can change its own input, and it is also called as a writing machine. So here also this can be the diagram on the which we can show. See the animation here. We can represent our Turing machine with the help of instantaneous description, transition diagram, and transition table. Okay, so right now I am postponing the explanation of instantaneous description. We will see in one of the problems after today's lecture, or in today's lecture, whatever possible. I'm going to tell you about transition diagrams and transition tables. Okay, so this is a transition diagram for this particular machine. So let's see how it works. Like it starts from Q0. It is reading 1, 1 is changed to 0, it goes to left and it's going to the state Q1. In Q1, if it is getting 1, 1 is changed with 0 and it's going to left. It's remaining in the same state. Like this, one particular diagram is there. There is no logic here for this particular problem, but with respect to the diagram, you can see how it is working. Okay, so here, see here, it is in the state Q0. In the state Q0, it is reading 1. This is an infinite input tape. It is infinite to the left hand side, infinite to the right hand side. Machine read head can go to left, it can go to right. Okay. So with 0, it's going to left. It is in the state Q2. With 1, it is going to right, and it is halted. Okay. So like here, they have shown it this particular thing. In Q0, in the state Q0, if it is 1, then 1 is changed with 0, initial state. So in the initial state, it will get 1, 1 is changed to 0. So it will change this 1 to 0. Okay, so it will change this particular 1 to 0, and it's going to left. So that is shown in the transition diagram, 1 change to 0 and go to left. So 1 change to 0, go to left. Now in the state Q1, it's reading 0. So in the state Q1, it is reading 0. So 0 ka transition is defined as 0 change to 1. And there is no, it is not going to left or right. So it is remaining here, but the state is Q2. So 0 change to 1 and it is in the state Q2. Now in Q2, it is getting 1. So for 1, 1 is replaced with 1 and it's going to right and it is going to the state Q0. So 1 is remaining 1, it's going to right and it is now in the state Q0. Now in Q0, if it is getting 0, 0 is changed to 0 and there is no move. But it is going to, means it is not going to left, it is not going to right. It is N and it's in the halting state. So 0 is changed to 0 and it is written, it is going to the final state. They have represented final state as QH. So it is a halting state. Okay. So this way it is working. So I'll go ahead now. Like here you can keep two numbers. To the left hand side you can keep a number A and you can keep another number to the right hand side and you can perform A plus B and you can perform addition of A and B and you can store the answer ahead, A plus B, or you can perform A into B. So like this it can act as a computing machine also. Okay. So we'll go ahead now in the next slide. Okay. So right now, please pay your attention properly. We are going, there are 20 minutes left. In the 20 minutes, I'm going to solve this problem. Okay. So now this particular animation is done by me to explain you how to solve the problem. Normally we do this with the help of a blackboard and I erase the symbols on myself and we solve the problem in the classroom. Okay, so I have tried my best to create my own animation now for the problem of designing of a raised to n, b raised to n, c raised to n. Okay, so assume that, so in the exam this way you need to solve the problem the way I'm going to show you right now. This is done by me, this is not ready-made animation. Okay, so I'm saying that machine is in the initial state Q0. In the state Q0 here, it is reading A. Okay, on the input tape, we have kept double A, double B, and double C. So here number of A's and number of B's and number of C's are stored on the input tape and they are equal. Okay, and machine is in the state Q0. Now after reading A, it will replace the small a with capital A. I'm using the same logic. Okay, you can have your own logic and you can use X, Y or blank letters, anything you can do. So I'm going to replace the small a with capital A. Then it will go ahead, it will replace the small b with capital B. It will go ahead, it will replace the small c, first C with capital C. It will go back, it will get the second A, replace the second A with capital A, replace the second B with capital B, replace the second C with capital C. It will go back. If there is any third A, it will replace the third A with capital A. It will try to find out third B and will replace third B with capital B and will try to find out third C and will replace with like this. It will go on doing it. Whenever it will not get any small A, that time it will go ahead. It will try to check that whether there is any B. If there is any B, that means number of A's and B's are not equal. So it will remain, it will go, it will be halted with an error or it will remain in the hang state. But if it is all A's are over and all B's are over and all C's are over, then it will get capital B. And in that capital B, then it will remain there and it will go to the final state by accepting the string. And here, this example is the example that shows you that the Turing machine is acting as an acceptor or recognizer for a particular string. It is not performing any calculation over here. Okay, we can design Turing machine for addition, subtraction, multiplication, division that we're going to see in next lectures. But here, this example is similar to finite state machine or push down machine. But designing a finite state machine for A raised to n, B raised to n, C raised to n is not possible. Designing the push down machine for A raised to n, B raised to n is possible, but designing to push down machine with A raised to n, B raised to n, C raised to n is difficult. Okay, so it's not possible. So Turing machine can do the problem easily. A raised to n, B raised to n, C raised to n ka problem. So we have taken that example. Okay, so now machine is in the state Q0 and there is a small a. Small a should be replaced with capital A. So what it will do? It is getting small a. So in the state Q0, it is getting small a. Small a is replaced with capital A and it's going to write, and it is in the state Q1. So in the state Q1, now it is ready to read a small a. For this a, it has to do nothing. It has to go to write. Okay. So we'll have the transition in the state Q1. If it is getting a, small a is replaced with small a and going to write. Okay. Now it is getting first B. So for one small b, you can draw the transition that b should be changed to capital B and go to right. Okay, so this small b changed to capital B and go to right. Now it is in the state Q2 and it is ready to read the next B. So now it means first it is getting the A. After that, it may get number of A's. For all number of A's, it has to go to right. Then it will get small b. So small b is replaced with capital B, and then it is going to right. Now it will get number of B's. So for number of B's, it has to go to right. Okay, so now it is getting small c. Small c will be changed with capital C, and then now it doesn't. It don't have to go to right, because the C corresponding C is changed to capital C. So now we go back again. Okay, from here it doesn't have to go to right because the C is changed to capital C. So after changing this C to capital C, it has to go back. So C will be changed to capital C and go to left, and it is going to the state Q3. Now what it has to do in Q3, it has to go back till it gets the capital A, till it gets the capital A. So for any symbol, it has to go to left. So we'll see that in this state Q3, if there is small b, it will go to left. If it is getting a capital B, it will go to left. If it is getting a small a, it will go to left. Now it is getting capital A in Q3. Okay, so here actually there is capital B is a confusion over here. So I have used this slanted capital B with the blue color to indicate a blank symbol, and capital B is my type symbol. Okay, now here in Q3 it is getting small a. So if it is getting a small a, that means it has to now start again doing the same operation which we started in Q0. So it will go back to Q0. That a will remain a, and it's going to write, and now it is in the state Q0. So it has to repeat the process. So now it has to repeat the process in Q0, it is getting small a. So all the transitions are already mentioned. So in Q0, with this transition, small a changed to capital A, it's going to write, and now it will be in the state Q1. Okay. So in the state Q1, now it is getting a capital B. So capital B ka transition is not mentioned in Q1. We are drawing the diagram right now by solving the problem ourselves. So Q1 may, if there is capital B, what it has to do, it has to go to right. So we have to write down the transition that in the Q1, if capital B is there, then go to right. And it is remaining in the same state. Now here it is getting small b. So small b ka transition is already mentioned in Q1, this transition. So this small b will be changed to capital B and it's going to state Q2. Okay, in the state Q2. So this small b changed to capital B, it is going to state Q2. Now in Q2, it is getting capital C. So capital C ke liye it has to go to right. So that transition is not mentioned here. So we'll say that capital C is changed to capital C and go to right. Now in the state Q2, it is in the same state. In the state Q2, it is getting small c. Small c ka transition is already done in the previous iteration. So small c will be changed to capital C, but it is going to the state Q3. Okay, so small c changed to capital C and it is going to the state Q3. Now in the state Q3, it is getting capital C. So in the state Q3, capital C ka transition is not mentioned. But for capital C also, it has to go back. It has to try to again, it has to go back till it gets the capital A. So in Q3, this for capital C, it will go to left. Now and it is in the same state in Q3. Okay, so now in Q3 it is getting capital B. Capital B transition is already done in the previous transition iteration. So for capital B it will go to left. Again capital B it will go to left and remain in the same state. Now it is getting the capital A. For capital A we have written down the transition in the previous iteration. So for capital A it will go to right and it is now in the state Q0. So in the state Q0 now it is getting capital B. Okay, that means all small a's are over. All small a's are over. So now the machine will go to right, it will try to check that whether there is any B or extra C. If number of A's are over, that means number of B's and number of C's should also get over. Okay, so in the state Q0, now if it is getting capital B, we say that it's going to right in the state Q4. And now in the Q4, it is getting the next B. So in Q4, if there is any capital B, it has to go to right. It should get all capital B's and all capital C's now. Okay, so if capital C is there, it will go to right. So even again, it is in the state Q4 and it is reading this capital C. For this capital C also, it will go to right. Now it will get okay. So now it will in the state Q4, it is getting this capital B. Okay, it will go to right, and now it is here and it is getting a capital B. For capital B, we say that if it is getting that, then that means when number of A's are over, there was no small b and no small c. So that means the string should be accepted. So in the state Q4, if it is getting a capital blank, this blank, then it has to stop. Okay. So we are showing that by using this transition that capital B is changed to capital B and go to left in the state Q4, and now here it is in the state Q5, which is a final state, and we have not defined any transition for the final state. And we have shown it by double circle. So when the machine reaches to Q5 in the final state, there is no transition, so it will halt by accepting the string. But if the machine is remaining in any one of the state, in the Q4, if it is getting a small b, that means number of b's are more than number of a's, and there is no transition for small b here. So then the machine will go in the hang state and it will reject it will halt by rejecting the string. Okay, so for this particular A raised to n, B raised to n, C raised to n, this will be the transition diagram. So in the exam, at least like this is a very important chapter. There are around 20 marks of paper questions will be there on the Turing machine, and they ask you to design the machine. You need to draw the transition diagram. Take the example and draw the transition diagram like this, and then you have to draw the table, transition table. This is the transition table. Okay, I'll just explain you because the time is getting over. I'll just explain you this. I think only 10 minutes are there. Okay, so this is the transition table. In the transition table, once the diagram is done, it's very easy to draw the transition table. So you will have all the states here. Okay, show the initial state in the transition table and show the final state in the transition table. Okay, I forgot to do that. Okay, I'll do that. Okay, so you show the initial state. This will be the initial state for your machine, and here this will be the final state. The final state you can represent uh, using a star or using a star or a circle. Okay, so this will be the initial state and final state. Okay, so in the transition table, you will have to show the write down all the states Q0 to Q5, all the states here vertically, and horizontally you need to write down all the tape symbols. So your input string is made up of small a, small b, and small c, and blank. and this is the way to show the blank symbol. Okay, so you can also show the blank symbol by small b and a slash over it. Okay, like this. Here, cancelled small b. This indicates it is a blank symbol, because here if we are using capital B as a tape symbol, then we should not use the capital B again here. So in that case you can show the small b slash, but it was difficult for me to do that here. That's why I'm just showing you in the transition table. Okay, and then these are the tape symbols. Capital A, capital B, and capital C are the tape symbols. So write down all the tape symbols here and all the states here, and then mechanically you just have to write create the transition table. Okay, so my suggestion is that in the unit test, if you don't have time, because for TCS papers it is very important to do the time management. So for the unit test, if the less time is there, if your diagram is correct, I'm going to give you the marks. Okay, so you keep this creation of transition tables at the end. If time permits, then only you do the transition tables. Otherwise, for the unit test too, if your diagram is correct, I'll give you the marks. But in the final exam, you have sufficient time, and you need to draw the transition table also. In the transition table, you see here Q0. See all the outgoing transitions. There are two outgoing transitions from Q0. So for both the transitions, you need to write down the entry in the table. So what is the entry for small a? Input symbol small a. So for input symbol small a column, you need to write down the output, that Q0 comma A. This is delta Q0 comma A is equal to Q1 capital A R. Okay. So here you see that Q0 input symbol is small a. So for input symbol small a, you write down here. What you have to write down the next state. Next state is Q1. Next state is Q1. Small a is changed with capital A. So here capital A, and machine is going to write. So write. Okay. So this is when you write delta, this is your left hand side. Delta Q0 comma A, which contains two elements. And this is your right hand side RHS, which contains three elements. So this is the previous state, comma A is equal to new state, new symbol, and either left or right or n. Okay, like here, this is Q0 if the symbol is capital B. So in Q0, if there is any capital B. So capital B may it is going to the state Q4, capital B is changed to capital B, it's going to write. Okay, this way you need to write down. This is done for Q0. Now for Q1, if you see how many outgoing transitions are there, here there is a loop and there are two outgoing transitions. So Q1 is going to Q1, but there are two outgoing transitions and there is one outgoing transition. So total three. So for Q1, you need to write down total three transition functions, and other things are blank or dash. Okay, so that means there is no transition. So Q1, small a to small a, comma R. So Q1 small a is changed to small a and R, and it's going to the remaining in the state Q1. Okay, this way you need to complete it. I think you have understood now. I don't have to explain you all the transitions. Now Q1 with capital B. Q1 with capital B is Q1, and capital B remaining capital B and R. But if it is in Q1, if small b is there, it is changed to capital B. So Q1 small b is changed to capital B. It's going to the state Q2 and it is R. Okay. So see here and write down the transitions in the transition table. For example, we'll see now for state Q3. In the state Q3, how many outgoing transitions are there? That 1, 2, 3, 4, and 5. Okay. So here Q3 may 1, 2, 3, 4, and 5 entries are there. And with small a, it is remaining in the same state. With small b, it is remaining in the same state. Capital B, it's remaining in the same state. Capital C remaining in the same state. But capital A, it is going to Q0. Okay, so capital A is going to Q0 from Q3. And A remaining A to R. Okay, this way you need to create the transition table. Okay, so I think you have understood the logic. So we will now in the from next lecture onwards, I'm trying to take as many problems as possible. I may take one extra lecture, one or two extra lecture if we have to cover the entire syllabus before Diwali. Okay. So be attentive and attend all the lectures because it is a very important topic, and there are around 20 marks of minimum 20 marks of questions are there on Turing machine. 20 marks of question on designing of Turing machine, and maybe 5 marks of question, 5 or 10 marks of question on the theory questions on Turing machine. So, so if your Turing machine is thorough, you can attempt around 20 to 30 marks of your paper. And if you are expert in that, you will get all these 30 marks out of your 80 marks. Okay. So be attentive, attend all the lectures, even if you are now in the pressure of doing or completing your submission work, and understand and solve as many Turing machine problems as possible. The book, which is a very good book, which is following the same convention, is your TechMax book of Turing, where they have given multiple practice problems of Turing machine with the logic. And for every Turing machine problem, if your logic is correct, and then your design is correct. So you need to remember the logic, and then you need to hand run the program, okay, and solve it. Okay, so see you again. We'll see this problem. If you're not, if you have you understood the problem A raised to and B raised to and C raised to and, please write in the chat box, and then I'll stop the lecture. Okay, mention, like, write down. I want your feedback. Have you understood Turing machine working?